The elements are also organized in S, P, D, and F blocks. These blocks represent orbitals with definite shape, determined mathematically through the solution of a wave function. Within these shapes are the high probability of finding an electron. In each of these orbital sets, there is the sequential filling of electrons from left to right. You may or may not remember how to write the electron configuration of any element or any ion using the S, P, D, and F orbitals. Here is an example. I will show you later how to write this in a much quicker way. The first two groups are called the S block. The S orbital has the shape of a sphere with the probability of finding electrons very high inside the sphere. The P block elements are the group 13 to 18. These are the 3p orbitals that are aligned along the x, y, and z axis. The probability of finding electrons at the nodal plane is 0. There is an equal and high probability of finding electrons in the colored lobes. The group 3 to 12 are the d block elements, and the 3d orbitals are filled on the first row. There are 5 d orbitals. 2 are aligned along the axis, and 3 are 45 degrees away. The lanthanides and actinides are the F block elements, where the 4f of the lanthanides are being filled, and the 5f of the actinides are being filled. The F block elements are all ionic. Fortunately for organic chemistry, the bonding is covalent, and only the s orbitals and p orbitals are involved, and these orbitals are often hybridized. We will discuss this later. As promised, the electron configuration can easily be written. Notice that the rows, these are technically called periods. I labeled these as row 1 to 7. Starting with row 1, fill the electrons. Row 1 is the 1s orbitals, going from left to right. Then go to row 2, fill the electrons. Row 2 is the 2s and 2p orbitals. Continue to follow this order. Let's take a look at phosphorus, element 15, as an example. It needs 15 electrons for the neutral atom. The element is in row 3, so row 1 and row 2 are complete. In square brackets, we can sum this as the neon's electron configuration, and to complete phosphorus, 5 more electrons are required. 2 for the 3s, fill it up, and 3 more for the 3p for a total of 15. So there are 5 valence electrons, or the outer shell electrons. In organic chemistry, the main focus are the carbon, nitrogen, oxygen atoms, with hydrogen and the halogens serving as terminal atoms. It is very rare to go beyond these elements to determine the electron configuration. In fact, we don't, and we only need to know the number of valence electrons, which is more important to know.